So if you were working with a code base, as you are, and you wanted to try to estimate how many bugs, to use a very colloquial term, or defects, discrepancies between what the software is doing and what it was supposed to do, as documented by requirements document or by design document, how might you go about estimating the number of defects that are in there? How many defects are in there? Maybe we found a certain number in the past week. How far do we have to go still? How would you estimate that? What's that?
You could look at how much code you've tested and how many defects were there.
Good.
Extrapolate from there.
I love it. I love it. And that technique, remind the name?
Evan.
Evan, yes. So you could start with code that you've already tested. You have some number of defects per 1,000 lines of code, and you say, okay, how much code do we have further? Now, it's a great idea, and this is called using historic data. Okay, this is one of 3 methods we'll be talking about. So here, we have some old defect density, and you're going to estimate a total number of defects by saying, here, what's the typical defect density? And you'll divide it by the density you've currently found in that code base times the defects found so far, and you will arrive at an estimate of the total defects. Primary problems for this are several-fold. One thing is past results may not be indicative of future performance and may vary by project. What sort of code might have more defects than other code? It might happen within the context of a given project that certain code has higher density of defects. Can anyone give me an example of code that would have a higher density defect?
Using assembly language versus something like Python.
Excellent. Excellent, excellent, excellent. Corey. Yeah. So there are big differences in language, particularly the level of the language. A couple of you are in my 470 class, and we're looking at the same basic program and multiple languages, right? We render it in C, we render it in Python, we're rendering it in traditional object-oriented Java, Next, and Java 8, and we're looking at it quite possibly from an aspect-oriented lens as well. Certain elements of it from an aspect-oriented lens. So often with different languages, you have very different defect counts. Why would that be? Language like C, what sort of defects do you think you might see that you wouldn't see in Java?
Seg faults.
Seg faults. Okay, what might a seg fault represent? That's a failure, and that's good. It's not the fault. What might be the underlying fault contributing to that? Remember, distinction between failures, which are manifestations of a problem, and faults, which are the underlying problem that gave rise to it. So we have failures, but beneath these are some faults. And a given fault might have multiple failures, might have no obvious failures. It might have a failure that's not obvious, it's not known, it's not visible easily. But what are some underlying faults that give rise to seg faults?
Accessing memory you don't have access to.
Yeah, so loose pointers, right? Pointers that point off into la-la land. So here we have a pointer and it's off to the heap. This is the heap here, right? And this pointer, maybe once upon a time, it pointed to a string. And then at some point that string was deallocated, right? And now you've got a pointer pointing to something in the heap that doesn't have anything there. Maybe something else gets later written over it, a big structure of some sort, or maybe it's code that gets put in here. Maybe it's code associated with bytecode for the Java. It won't be for the Java virtual machine, but some sort of code that is your compiled C code. It's machine language code, and then you write to this pointer. Bad things happen. Well, that's one way you can get a loose pointer. What's another way you can get a loose pointer in a language like C? For those who are in 470, I mentioned this morning. What's another way?
Pointer arithmetic.
Indeed, indeed. So here you have your, say, an integer array, and here you have your pointer, and then you start performing pointer arithmetic on it. P++, right? Now it points to here. P++ points to here. And you keep on plussing your P, and eventually it might point out to here, And it's pointing out into an area that's beyond this area for which it was allocated or from which it was obtained. And it may start to point to other things, including, well, in some systems, some embedded systems, parts of the operating system. And you write to that pointer, and bad things happen with a capital B, and often with a capital A and capital D too. Like it crashes the operating system, which in my world at least is generally considered bad. So you can have a loose pointer here. So that's good. That's a bug. What's another bug that can happen? Silent but deadly, but eventually causes things to blow up in something like C.
Memory leak?
Memory leak. So we start to have all this memory allocated, and these things aren't even paid attention to anymore, but they live and fragment our memory. And eventually, think about on a small device, a smartphone or a embedded system that's running like IRD makes, International Road Dynamics in town up off of Millar Ave. They make these devices which sit roadside and use embedded processors and so on. And you might have this thing filling up with memory, and eventually it runs out, and it says memory exhausted. Those are bad things that can happen in C and can cause significant defect density per unit of code. They do not happen with Python, and they won't happen with Java either. Okay, good. So different languages have different defect densities. Very good point. Language like Prolog to solve problem. You're going to often have a very crisp description of certain problems. And maybe parts of your system are written in JavaScript, parts of your system are written in Swift, parts of your system are written in Java on the back end, Java struts perhaps for web-based programming, or maybe you're using Django and you're using Python on Django. So you might have different areas of your program with different languages, right? So different defect densities for those. What's another reason you might have very different defect densities for different areas of code? Some code's newer than other code, right? Some code was rolled out a while ago. It's been tested. It's been used by the user. A lot of faults have been found, and now you've got code written by a new set of people with new technologies, with improved testing set and so on, and it's hard to compare it. So, ladies and gentlemen, defect estimation based on historic numbers, great stuff. Can be very very insightful, but it has its limits. Let's talk now about a second technique. This technique here. It's number 2 here. Defect pooling. Okay. Actually, both of these really, defect seeding and defect pooling, both relate to this. Okay. So imagine we have a lake or a big slough. Okay. So here's our big lake, and we want to estimate the total number of fish in it. I'm going to draw an analogy between this and finding bugs. So we have in our lake here some number of fish, and they're swimming around. There are some lunkers and some small ones, and we want to estimate how many fish there are. And all we have is some fish tags. And what these fish tags allow us to do is to tag a fish in a fairly innocuous fashion, so that if we catch that fish again, we can recognize it's a fish we caught before. How could we estimate number of fish in this lake or slough using those fish tags? So we have a tag, and we can tag particularly fish so that we know we've seen them before. How could we estimate the number of fish? So we have a net and we have some fish tags. What could we do?
You could just catch a bunch of fish, tag as many of them as you can, throw them all back, and then let them all disperse and run around, and then just catch a bunch again and see how dense your tags are amongst the new ones that you catch.
Great idea. Great idea, Russ. Okay, so the idea here is that we could go through 2 phases. And these phases actually can be undertaken at the same time, which we'll come to. But the idea is for software, they can be undertaken at the same time. So we tag a certain number of these fish, we put them back in, and then maybe a day later, after they've dispersed and moved around, if not run around, we go back and we find them, right? We go back and catch fish again. So tell me, let's suppose that we did that. We had our net, we caught all these fish, we tagged them, and we threw them back in. And the next day we come and we drag our net and we come up, so the first time maybe we had 100 fish. This time we come up with 100 fish, and there's only one of them that we see now that was tagged yesterday. What would that suggest about the number of fish? Putting aside the actual numbers, what would it suggest about the number of fish in the pond?
There's probably somewhere on the order of 100 times the number of fish that you originally caught the previous day.
Good.
So maybe
10,000 or something like that.
Yeah.
Okay, because after all, we have the new set of fish, and only 1 out of 100 of them was in the group we had yesterday. So probably for each of those fish we caught originally, each of those 100, there's probably 100 more. I mean, you could fault the statistics of it in terms of, well, it's not exact, but yes, but it gives us a sense it's a lot of fish out there. It's a lot of fish, right? Maybe for each of the original fish, maybe if we're far off, there's 50 for each of them or something like that, but there's still thousands and thousands of fish. Let's suppose, by contrast, ladies and gentlemen, those fish that we caught that first day, let's suppose that we catch these fish on the second day with a similar net and everything, second day, and virtually all the fish we catch on the second day, all but 1 or 2, were ones we caught in the first day. What would that suggest about the number of fish out there in the pond?
We just caught all the fish in the pond.
Yeah, we're getting pretty close to a complete catch of fish, probably. And again, we may be missing a few here and there. And if we're dragging on the exact same area of the lake, then maybe we're just getting fish in that area. But we're getting a pretty complete set of fish, at least given within the parameters of the catch. So that's the rough idea here of these techniques. Okay. Okay. So let's give this example. Okay. So suppose you caught, tagged, and released 50 fish. Then you caught 100 more fish, and you found that 5 of the newly caught fish out of the 100 are found to be tagged. How many fish do you think there are in the pond? So again, you've tagged 50 fish there, and you caught 100 more, and only 5 of those were tagged. How many do you think there are in the entire pond? Well, for every one of these 5 tagged fish, how many fish are there total? For each one of these 5, there are 20 times the number, right? So there are 100 fish you've got this second day. Only 5 of those are tagged. So for each of the tagged fish, including that tagged fish, there's a total of 20 represented, right? And so you might think, well, for each tagged fish caught and released that first day, there's 20 more. There's 20 more out there. 20 more out there. For each tagged fish, there's 20 fish out there. So for each of these 50 fish, there's 20 fish in the pond. That's a sample of 50, but there's roughly 20 times that, because 10 divided by 5, right? For each of these tagged fish, there's 20 fish in that, as we caught it the second day, and so we'll think that for each of these 50 fish we caught the first day, there's probably 20 out there. So how many fish? 50 times 20, or 1,000, yeah. Okay, so, another way to think about it is in terms of fractions. Since we caught 5 out of the 50 fish within the later catch. We estimate that's the fraction of all fish we caught in this later, in the later catch. We caught 5 out of 50 of all the fish in the pond, and 5 out of 50 is 1 out of 10, right? And therefore we caught 100 fish, and therefore there's probably 1,000 divided by 0.1 or 100 divided by 0.1 or 1,000 fish out there. Okay, so what are some of the assumptions about this? I mean, it seems like a common sense strategy. What are some assumptions that we're relying on here? Why isn't this perfect?
You're assuming the fish are evenly dispersed.
Yeah, you're assuming the fish are evenly dispersed, that you're not catching just from the same rock that you did yesterday, so you're only catching fish in that area. You're assuming the fish, migrate, mix equally throughout the pond, and so you're getting a kind of random sample of it. And then there's some statistical variability, right? There's some statistical variability maybe we caught 5, but we could have just as well easily caught 4 or 6. And so there's some variability in our estimate for sure based on the happenstance of what we caught, right? So we are making some assumptions. We're not just catching less elusive fish or only the large fish, the rest slip through or what have you. Okay, so what I'd like to suggest here for this is running a bug party. And the idea is you have 2 different teams running a bug party, folks. We're going to see how this happens. Let's talk about defect pool, and we'll see how those 2 teams on a bug party could help you estimate the number of bugs out there. So the idea here, folks, is that you're going to engage in a process called defect pooling. So you're going to have one team, Team A, find one set of bugs, and that same night, if possible, a second team find another set of bugs, independent of each other. They're going to be working in different areas of space. They're not talking with each other. They're not saying, oh, I found these bugs in this area of the program. And what you look at is the overlap. Okay? Now, if this overlap, let's suppose that you have your team and someone else has their team, and there's just a small overlap between them. What would that suggest about the total number of bugs out there?
There's a lot.
It's a lot. It's kind of like, the fish that are tagged being only a few fish are tagged in that group you catch that second day, right? If there's very little overlap, there's a lot of defects out there. If there's a huge amount of overlap, maybe you're getting most of the defects in your catching this. That's in the 2 team what the 2 teams have caught. So can anyone come up with a strategy using the mathematics we came up with for defect for the fish? What strategy would we use to estimate the total number of bugs here? So suppose Team A in a highly productive series of nights comes up with 400 defects, and this one 350 defects, and there's an overlap of 150. What might we estimate the total number of defects to be by analogy with the fish? You don't have to come up with a number. Give me a formula. I'll give you a clue. The formula has all 3 of those numbers in it. We'll start with 400. This is like, let me give the analogy. This 400 is like the number of fish we caught on the first day.
400 minus 150.
Sorry?
You start with 400 minus 150.
Okay, I like the fact you're weaving in the 150. Turns out we're not gonna minus it, but there's another operator we're gonna be applying to it. So again, let's use this analogy. Okay, for each of these defects that they had in common, for each of these 150 defects they had in common, there were 350 other defects found in, or 350 total defects excuse me, for each of the 150 defects found in common, there were a total of 350 defects found by B. So for each of the 150, there were 350 divided by 150 that existed as identified by pool B. Okay, that's for each of the 300 of the 150 found. This is the sort of number of defects per number of defects found by Team B per common defect found. Okay, so how could we use that to estimate the total number of defects? Well, it turns out that the underlying mathematics of it are the same as in the case of the fish. Okay, so the total number of defects here are just the defects in pool A times the number of defects in pool B divided by the defects in both pool A and pool B. Okay, so here we have these 150 defects in both, right? And the case is very clear. Suppose you only had one defect in common. For each of those, there's 150 others that B found. So for each of these 400, there's 150 others. So if we only found one defect in common, it would be, we'd have a total of 350 divided by 1, because this is the number in common. This is the number in common. So we'd have that as the total number of estimated defects. If all there was one in common, we're saying for each of the 400, there's probably 350 others. By contrast, ladies and gentlemen, if this 400 had a huge overlap with the 350, say all of the 350 were part of the 400, then we would estimate, okay, there's going to be a total of 350. If every single one of those 350 that were found by Team B were already part of the 400, then we'd estimate we've gotten all of the defects, all 400 of them. Here we only have one in common, so we have a much larger number of defects, 400 times 350, right? Which is what, 70,000, something like that. So here, ladies and gentlemen, excuse me, 140,000? Yeah. 35 times 4, right, 140,000, yeah. So obviously there's a big difference here, but the idea is how many defects do we have for each of these ones in common? How many defects did Team B find total? And we multiply that times the number that Team A found. And it's symmetric. You can do the same thing in the reverse. Talk about finding the 350 and how many of those did Team A find, etc. So this is the underlying mathematics of it. Number found by Team A times the number found by Team B divided by the number that are in both pools A and pool B. Does that make sense to people? Are people comfortable with that? I see a number of heads nodding. Are people okay with that? So let's talk about it. Obviously, this has some challenges, but this is the analogy with the fish case. Here, the number in both corresponds to the fish that were caught in both rounds, right? So the number here are fish caught in both rounds A and B. This is round A, round B, and you have the same underlying mathematics of it that led us to that estimate of 1,000 fish earlier. Okay, and we phrased it like this before, which turns out mathematically to be the same formula. Okay, so let's talk about defect pooling. The idea here is, again, you should have two teams working independently without communication. You could do it in a single night with 2 or 3 hours, and you should be testing not just a small piece of the software, just like you don't sit and cast your net from one particular rock and depend on that. You trawl the entire space. So you test the software fairly broadly, and and then you will go and record the bugs that are found. Enough so that you could recognize if those same bugs are found by the other team. So you record how many bugs your team found and what those bugs were. They record how many bugs they found, what those bugs were in terms of the failure modes, not yet having debugged them. We can't say what the faults were, but at least the failures. And then you can apply the basic mathematics, this formula. Okay? And you should be able to arrive at an estimate of the total number of defects out there in your software. It's not perfect. There are assumptions associated with it. Assumptions associated with certain bugs being equally easy to find. The fact is, in both teams, you're going to be finding easier bugs. You probably have a lot of bugs that are found, not because they're totally representative of all the defects in the program, but because they're easy ones to find. They're simple ones to locate. They're obvious ones. But it will at least give you an order of magnitude estimate for how many defects are out there. And it's very doable. And I would suggest having a bug party to do that. Go and have a bug party over in Spinks. Maybe bring some pizza and see if you can find common and disjoint defects and estimate the total number. Okay? So very actionable. You could do it this week if you wanted to try to estimate defects there. Now there's another technique known as defect seeding that does the same thing. And this technique enjoys greater delicacy associated with it, but it's the same basic idea. The idea here is even more direct analogy to fish. The idea is you actually insert defects into the software. How could that possibly be the case? So you deliberately introduce defects and, of course, record where the defects are you've introduced. And then what do? How could that help? How could it help identify the number of defects you didn't introduce?
We'll just get a different team to just try to find all the defects they can and then count how many of those were ones that were intentionally produced.
Exactly. So you go and you introduce these defects and then you run your tests, manual, automated, and you see what fraction of the defects that are found are in fact these seeded ones. Let's suppose that only one of the defects found is a seeded one. All the rest are unrelated. What does that suggest?
You have a lot of bugs.
You have a lot of defects in the system. That's right. You're barely scratching the surface for finding the defects. If by contrast, all the defects you found, having done this, are seeded defects, you may be doing pretty good. No guarantees. There may be areas of the program you're not yet really testing well, but it gives greater confidence that there's not a huge number of bugs out there you're not finding of similar sort. And then, of course, in the final step, you do what? You remove the defects you seeded. Of course, right? With the careful notes that you have taken. You don't want to leave these defects in there. Now, there actually are tools that will insert defects into your code base for this purpose, to test your testing. They'll actually test, what sort of coverage, not in a sense of lines covered, but in a sense of actually finding defects. What sort of coverage are you getting? That could include the results of manual testing. How much are you really picking out these bugs? Defect seeding can aid you with that, and there are tools that will automate it, that will seed bugs in there, and of course let you run your tests and remove them. Okay, fairly straightforward. You'd be introducing defects of different sorts, different levels of severity, different types of bugs, and broad areas of functionality of the system. And you seed prior to the test, right? And then you run a suite of automated tests and manual tests. So what are some caveats of this? Well, obviously you need to remove the bugs that you seeded. Another thing is that you have to catch these reports at time of sanitization. What do I mean by sanitization? Remember back there, I do expect you to remember that thing. What is sanitization? What is bug sanitization? Remember the stages of a bug's life, the defect's life. What are those stages? What are those stages? Remember, there's, we're going to draw this out. It's in one of my earlier slides, but okay, so these are all these are unknown defects. These are ones that aren't yet recognized, right? They're not reported. They're out there. They're latent, but you don't see them. What's the next stage? There's reported defects, right? Those that are reported, but they're not yet sanitized. Reported, but they haven't gone through sanitization. And this step is called sanitization. And what is that step? It's a very key step. And one would desperately hope that you are doing it right now. You're going through a sanitization process. Because you may have defect reports, but it's hard to weigh the seriousness of these defect reports until you do sanitization. Give me some examples of things that sanitization removes. Bug sanitization.
It'll take the reports and find out if it's something that you already know about.
That's right. So you're gonna get rid of duplicates, because quite often what someone has reported was reported before, and that's great. We know that people are seeing it multiple times, that it's reproducible. Maybe they report a different way of reproducing it, but you don't want them treated as separate bugs. So one thing is remove duplicates. What's another thing you remove there?
Things that are actually bugs.
That aren't actually bugs. So this is things that are misunderstandings. Now, the fact that there is a misunderstanding might tell you something important. Like, real world users might have the same misunderstanding about how this feature operates, but it's not a defect in the code to be fixed. So I would pay attention to these strongly and ask, do we need it to be a feature request or a request for improvement in documentation? But it's due to misunderstanding. What's a clearer thing that you want to remove? Well, something that's been fixed, not necessarily because it was a duplicate of another bug, but maybe you've replaced your entire area of the code that depended on one technology with another. You've converted the system. Instead of using this clunky library you were using earlier, you've converted it over to use another library. Or you've rewritten that code since this bug was first introduced. So you can have things that are fixed, things that are outdated, in the sense that they were, and this often goes together, they respect to an old version of the software. Maybe it isn't fixed, maybe that function isn't there anymore because it's been replaced. It wasn't technically fixed, it was just deprecated, but they're outdated. They're obsolete, in other words. So, these would be sort of obsolete bugs. So all these cases, you're going through sanitization. And this might be a reduction by a factor of 2 or 3 before it gets into this set of active bugs. Okay? And then there's a process of triage, which is going to figure out, are these bugs to be fixed? And again, why wouldn't you fix a bug? Okay, you find this a failure. Why wouldn't you fix it?
Perhaps it's relatively minor and would be just require a huge amount of time and effort to fix.
Good, I like it. It's minor and there's a lot of effort, a lot of rejigging of the software that would be required to fix it. And why might you hold off on that? Because that rejigging of the software, that effort to fix it, it requires a lot of work, and that work has an opportunity cost. It takes you away from something else. Mm-hmm. So that's one reason. Give me something else besides the opportunity cost that's at issue. It's the elephant in the room with software. Sorry?
Stability?
Yeah, it's risky to fix it. Who is that? Howie, thanks. I can dimly see faces. So if I squint, I might be able to make you out. So just as Howie said, there's a potential that it destabilizes things. That fix you put in actually causes other problems, right? And one of the biggest issues, ladies and gentlemen, is that you don't have the luxury, you don't have the time to test it and to debug it at this point. So you may be, 3 days away from the delivery deadline. And yes, you could fix it maybe in the next day, the next 2 days, but you don't have time to run your tests against it after fixing it. You don't have time to run the full suite of tests. You don't have time to do manual testing against it. There just isn't that time. And that destabilization, as Holly says, could be critical, because now you're basically rolling the dice. Do you feel lucky today, right? Fixing that bug and not having a chance to test that? Or would we rather stick with the devil we know? Would we rather stick with this defect that is a recognized defect we can warn the user against, we could suggest workarounds, we can put in place mechanisms that will make it less likely the user will hit it. We could put in checks that will warn the user if a problem has occurred. We can educate things versus a situation where we don't know what the defect is. We don't know if there are defects because we haven't had time to retest it thoroughly. We haven't had time to have the testers really pound on it. This is a big issue for software. So you hold off on fixing it because it's too risky to fix. Too risky because you don't have the luxury of retesting things. Can't tell you the number of times I've deployed software where this has been on my mind. And I've held off fixing things for this reason. We can educate the user about things we know about, but not about things we don't know about. And I'd rather go with a defect of known modest severity to something that could be really bad, we just don't know. I remember one guy I met in the professional software development world. In high school, he had sold software to a manufacturing plant. I think it actually was a power plant authority. I think it may have been like accounting software for their human resource division. This software was written by a high schooler, and it didn't have a lot of good testing. And he found a number of defects. He was working at these defects. To the last minute, he had to go to the airport to fly to the customer's site. And he didn't have time to test the software. After fixing, he was fighting with his bug. He didn't have time to fix it. He compiled it, and he went to the airport. He had no idea, is this going to work or not? So he flew to the customer site, and they introduced them, and they asked him, okay, could you give a demo of the software? And he went in front of this crowd of folks at the software company to give this, at this power company to give this demo of the software he hadn't had time to fix. And he went in front of them as a desperate chancer, and he started it, and it worked. Actually, it worked. He was sweating bullets, I think, the poor guy. But you don't want to be in a situation like that. Maybe you have been in a situation like this. Maybe in this very room. Okay, I won't go there now. Okay, maybe a bit too close to home. Are these sweat marks on the floor over here? Anyway, the point is we don't want to be in that situation. We want to have time to do adequate testing of a system after we deliver it, or after we fix bugs. And often we don't have time, and therefore we hold off fixing bugs. Okay. So one issue with defect seeding is that we have to catch it at this stage, ladies and gentlemen. We have to catch it at the sanitization stage. We don't want this to be listed as an active bug to be fixed, and work to be going on about thinking how we're going to fix this when it's something we need to remove, right? Another problem is that attempted fixes for seeded bugs can cause new problems or hide other problems. In fact, seeded bugs themselves might hide problems that otherwise would be found. So an introduced bug might prevent you from executing certain functions of the software that would otherwise show bugs. So it's not, they're not independent of each other. There's some issues there in terms of estimation of this. Sometimes it can also cause resentment. You know, you introduce a defect, or the software automatically introduces a defect into an area that someone wrote with great care, and now suddenly there's a bug reported in their code. There can be bad feelings that come from that. So suggestions here: keep seeded defects simple if possible. Use an automated system for introducing and removing them, and of course eliminate carefully. Okay. So defect seeding, a valuable strategy for estimating the number of defects out there. Okay. So that's good, ladies and gentlemen. I'm going to. Time is limited here. I'm going to go on to the next bit of discussion, but only in kind of a